Oscillations.
Today we have to derive the expression of energy of a particle when performing the simple harmonic motion. But for that, you know the meaning of simple harmonic motion. Here, simple harmonic motion is nothing but the to and fro motion. It means that suppose here if we consider this will be the one of the straight line path, then here that particle which performs the to and fro motion, and that to and fro motion is nothing but the simple harmonic motion, right? Suppose here this will be the path of a simple harmonic motion, and in that path, suppose if we consider this will be the main position. O represents the main position, and now this will be the extreme right position, and this will be the extreme left position. Here, the distance of point A and point B from the main position is, suppose that distance is plus A, right? It means that towards the positive side, there we get the distance is plus A, and towards the negative side, that is the towards the point B, that distance is there minus A. But here plus A and minus A represents the amplitude of a simple harmonic motion. Right? Now, during the simple harmonic motion, suppose that if we consider one of the position, suppose position is P, and the distance of position P or point P is x from the main position. Then at point P, how much amount of energy is produced, we want to find out that, right? But you know the formula of the total energy. What you get there? Total energy, which is equal to the, what you get there? Kinetic energy plus potential energy, right? Suppose that if we consider this will be the equation number 1, then first of here we want to find out the value of kinetic energy at point P. So kinetic energy, what you get there? The formula of simple kinetic energy, which is equal to the half of m into the v square. Here m represents the mass of a particle which performs the simple harmonic motion, and v is the velocity. That is velocity at point P. But we know the formula of velocity in linear SHM. What you get here? Here the value of Vp, which is equal to the, what you get there? Omega into the under root of a square minus x square. So this is the value of velocity at point P. Point P is the in general point, right? So that's why there the velocity of a particle at point P is omega into the under root of a square minus x square. Suppose that if we substitute these values in this equation, then what we get there? See here. So kinetic energy, which is equal to the half is as it is, m which is also as it is, and now we want to take the square of this Vp. So what we get there? Omega square, and again here the square of under root get cancelled. So simply what you get there? Inside the bracket a square minus x square. Right? So this is the formula of kinetic energy. Again, here instead of m omega square, again we substitute the value is k. But what you get there? K, which is equal to the m omega square. Now substitute this value here. So kinetic energy, which is equal to the half of k into the a square minus x square. Right? So this will be the value of kinetic energy of a particle performing the simple harmonic motion at a point P. Suppose this will be the equation number 2. Now we want to find out the value of potential energy. Now potential energy. But we know the with the particle performing the simple harmonic motion, right? At that time, inside that motion, there the restoring force is stored, and a against that restoring force we displace the particle. Against the force we displace the particle, means their work is done. So here whatever work is done, so that work done which is stored in the form of potential energy. So that's why here instead of potential energy, first of all we want to find out the work done. Suppose that if we displace the particle from point P to suppose point Q, and the distance between the point P and Q is suppose there dx, it means that if we displace the particle in linear SHM by the distance is small, that is a dx, then how much amount of work is done? We find out that, right? So here the small work done for to displace the particle from point P to point Q, work done in between the point P and Q is what you get there. Here distance is small, so that's why their work done which is also small, and small work done which is represented by the letter is d omega. Yes, here the basic formula of work done is force into the displacement, that is F into the dx. But what happened here? The direction of restoring force and the direction of displacement which are opposite to each other. Here the direction of restoring force is always towards the main position, and now we displace the particle against that main position. So that's why in between this one here we give the negative sign. Negative sign indicates that restoring force and displacement which are opposite to each other. But the value of force is internal restoring force is what we get there, F which is equal to the simply minus Kx. Here K represents the force constant and X is the displacement. Now we want to substitute here. So what we get there, dW which is equal to the what we get there is minus, and again the value of force is minus K into the X, and now this dx is as it is. What happened here? Minus minus get a plus, right? So what we get there? Therefore dW which is equal to what we get there, K into the X into the dx. So this much amount of work is done for to displace the particle from point P to point Q. But here our target is we want to find out the work done for to displace the particle from point O to point P. Right? For to displace the particle from point O to point P is. So there total work done. So what we get there? Total work done is which is representing by the simply W. So total work done W which is equal to what we get there, integration of dW. Here we want to displace the particle from point O to point P. It means that from distance 0 to distance x. So that's why here we want to give the limit, that is from 0 to x. And here the value of dW is what we get there, kx into the dx. So what we get there? So integration from 0 to x, here kx, right, and the dx which is also as it is. But we know the rules of the integration. We keep the constant quantity outside the integration sign, right? So this is the rules. So what you get there? So total work done W which is equal to the K. So the integration from 0 to x into the x dx. And now we want to integrate this x. But we know the rules of the integration. In integration, the power of variable which is increased by 1, and again we want to dividing the same quantity by the new power. Here the power of x is 1, so their new power is increased by 1, so 1 plus 1 is 2. It means the new power is 2 and we want to dividing by the same power. So that's why the integration of this one. So W which is equal to the K inside the bracket x square by 2. And now here limit is from 0 to x. Right? So this is the integration of x dx. Here we want to keep this 2 is outside. So what is it here? So work done W, which is equal to the half of K. And now here we want to substitute the upper limit, then lower limit. Here the value of upper limit is x, so that's why x square. Here the value of lower limit is 0, so what to get there? Minus 0. 0 square is again 0. So what to get there? X square minus 0. X square minus 0 is not equal to simply x square. So that's why what to get there. Therefore, work done W, which is equal to the half of K into the x square. Right? So this is the value of work done for to displace the particle from point O to point B. But what happened? This work done, which is stored in the form of potential energy. So that's why this work done is nothing but the potential energy. What happened here? But potential energy, which is equal to the work done, and the value of that work done is half of K x square. So this is the formula of potential energy at point P. So suppose that if you, this will be the equation number. Now this will be the second. And now this will be the equation number. Here we find out the value of kinetic energy. We find out the value of potential energy. It means that we want to substitute equation 2, equation 3 in equation 1. Then we get the total energy. Now put equation 2 and 3 in equation number 1 we get. See here, what we get there? Total energy, which is equal to, here the value of kinetic energy is what we get there? Half of K into the A square minus x square. Right? And the value of potential energy is what we get there? Plus half of K into the x square. If you see this equation, then in that what happened? Half of K is common, so take outside. So what we get there? Therefore, total energy, which is equal to the half of K. So this will be the common. Then inside the bracket, what we get there? Here A square minus x square, A square minus x square, and from the second term what we get there? Plus x square. What happened here? This minus x square and plus x square get cancelled. Simply here we get the a square. So what we get there? Therefore, total energy, which is equal to the half of K into the a square. Right? And now this will be the equation of total energy of a particle when performing the simple harmonic motion. Right? So this is about the total energy at point P. So this is the in general equation of the kinetic energy, potential energy and total energy in linear SHR. Right? So this is about the energy of a particle in linear SHR. Thank you.